In this video, I am going to give a brief introduction about our recent paper AdaCon, which is Adaptive Context-Aware Object Detection for Resource-Constrained Embedded Devices, and then I am going to show a demo to illustrate how it works. The main idea behind AdaCon is to use the information from the spatial context around the objects in order to make the object detection tasks simpler, which means that we can use the spatial context to infer which subset of the object categories can exist in the current frames with high probability. And since the task is now simpler, we can only execute parts of the network, which will consequently reduce the number of floating point operations and the energy and the latency, making the model more efficient. Before going through the architecture of our adaptive object detection model, I'd like to give a quick review about the general scheme of most modern object detection models. So for object detection models, the input is an image with some objects, and the goal is to determine what are those objects and where are they located in the image. So for most modern object detection models, the first component is the backbone, which is basically some consecutive convolution layers that can extract some features from the input image. Those features are then parsed to the detection head, which in turn detects the objects and their locations by a bounding box surrounding the object. For our adaptive architecture, we added a branch controller after the backbone, and we replaced the detection head with a pool of detection heads of smaller size. Each head is responsible for a different spatial context. And during runtime, the branch controller will choose which branch or branches to execute based on the spatial context of the input image. Now I am going to show a demo to analyze the efficiency of our AdaCon model and compare it to the static baseline. To test the efficiency of our AdaCon model, we deployed our model on an Nvidia Jetson Nano board. The specs of the Nvidia Jetson Nano board is typical to modern embedded devices. It has a low-power embedded GPU, a quad-core ARM Cortex CPU with 4 GB of RAM, and it uses 5 to 10 watts depending on the workload. For the purpose of this demo, we recorded 2 different videos for different setups, and we analyzed the latency and the energy consumption of the Nvidia Jetson Nano board. The video to the right shows the baseline, which is RetinaNet, and the video to the left shows our AdaCon model. So we can see clearly that the latency of our AdaCon model is lower than the latency of the baseline model, with around 100 milliseconds, which is almost 25% of the latency. Also, the energy consumption of our AdaCon model is 30% less than the energy consumption of the baseline. Similarly, for the indoor setup, our AdaCon model has less latency and energy compared to the baseline model.